We write code using text. We use words, variables, and logic that map to human reasoning. But the hardware executing that code only understands binary states, voltage gates flicking open and closed. The human-readable text is an illusion. When you write a simple assignment like x equals y plus 1, you see a mathematical relationship. To a compiler, x and y are initially just character strings. The language processor's task is to bridge this gap. It must take those character strings and translate them into exact physical memory addresses on the hardware. The rules governing this translation are laid out in the canonical text on the subject: compilers, principles, techniques, and tools. To understand how this translation works, we have to examine the boundary between static and dynamic policies and break down how environments, scopes, and parameter passing operate in memory. Mapping names to locations is the primary mechanism the compiler uses to build a consistent model of memory. The first boundary in language design is determining when the compiler makes a decision. If a rule can be enforced by analyzing the text before the program runs, it is a static policy. If the decision requires the program to be executing, it is a dynamic policy. To manage variables, compilers use a two-stage mapping system. They separate a variable's identifier from the data it holds. This chart outlines the process. Stage 1 is the environment mapping, binding a name to a specific machine location, the L value. This mapping is governed by static scope rules. The physical location bound to a name changes based on where you wrote the code. Stage 2 is the state mapping, binding that physical location to an actual value, the R value. State mappings are strictly dynamic. As the program computes new data, the value at a location updates continuously, even while the environment mapping remains static. This two-stage mapping ensures that the logic of the source code remains intact, even as the underlying data is reorganized during execution. In the C family of languages, the environment is defined by block-structured scoping. This is a spatial system. This diagram shows 4 nested blocks of code. When the compiler resolves a variable request, it uses an inside-out search algorithm based on these physical boundaries. If the program prints B from inside block B4, the algorithm searches that block first. It immediately finds a local declaration of B and binds to that environment. But if B4 requests A, the process changes. B4 has no declaration of A. The algorithm expands to the enclosing block B2. There is no A. It skips block B2 and stops at block B1, binding to the declaration found there. Object-oriented languages overlay explicit access controls on this. Keywords like public, private, and protected act as restrictions on this geometry, blocking the search algorithm from accessing certain locations. Because the system relies on the physical layout of the text, static scoping provides predictability. The compiler maps every variable to its precise memory location before the code is executed. What happens to the environment mapping if a language dictates scope by time instead of space? This is dynamic scope. A primary example of this policy occurs during macro expansion in the C preprocessor. In a dynamic system, the compiler does not search the surrounding text. Instead, it searches the active call stack during runtime. The environment binds the name to the declaration inside the most recently called active procedure on the stack. It bypasses any deeper global declarations. Dynamic scoping sacrifices the predictability of compile time analysis for runtime flexibility. Under this policy, variable resolution is dictated by the execution history of the program. The mapping of names to locations becomes more complex when procedures pass arguments. The two-stage map exposes the mechanical difference between call by value and call by reference. In call by value, the caller evaluates the actual parameter's R value and copies it into an isolated memory location assigned to the callee's formal parameter. This isolation ensures that the callee's operations cannot mutate the caller's original memory location. While Java is strictly call by value, when it passes objects, the value it copies is a reference or pointer to that object. By copying a pointer's value, the system creates 2 distinct environment locations that both end up converging on a single shared state mapping. Call by reference operates differently. The caller directly passes the actual memory address, the L value of the parameter, bypassing value duplication. The mechanical result of call by reference is aliasing. 2 different variable names map to the exact same physical location. Mutating a formal parameter in an aliased environment permanently overwrites the caller's data because both names point to the same location in the store. The compiler must align the hierarchical structure of a program with the sequential instructions required by the hardware. As a program runs, environments expand and collapse, and states update endlessly, all overlaid on the static, unmoving grid of physical silicon. Tracing how a language binds names to locations makes behaviors like aliasing and shadowing predictable consequences of the language's design.